Very last section in chapter 1, section 1-6. It's usually one that we just do all in one day, so no parts here. This is just it. Don't forget, we are planning on a quiz tomorrow over 1-4 to 1-6. And it will probably be in two parts again, like last time. Part 1, no calculator. Turn it in. Part 2, you can have a calculator. But you can make just one-sided half cheat sheet that you get to use for both parts. And I'll give you a handy dandy if you need that also. But don't forget about that. Yep.
Is our test going to be this year?
Either Thursday or Friday. I haven't decided yet. But yeah, it'll be probably Friday, I would say. You may have a couple review days. Is that all right with you guys? Is there a field trip I should know about? Okay, good. All right. Now, the title of this section is actually really important. Limits at infinity. Taylor said it perfectly when she walked in. She said, "Isn't that what we've been doing this whole time?" Well, yeah, I mean, it kind of does sound like that, I'll be honest. So that is a good point because I'm going to first talk about the difference between what we're learning today and what we have been doing this whole other time. It does sound like the same thing. So, limits at infinity, that's the new stuff. And I put not to be confused with infinite limits. They sound very much alike. Limits at infinity, not to be confused with infinite limits. I'm going to go through just a couple things about each one, and then hopefully once you see these differences here, you'll understand which one's which. Kind of hard to remember though, limits at infinity versus infinite limits. So I'm going to start with infinite limits. This is what we were talking about in the last section. So pretty much just like what we were doing on Friday when we were increasing without bound, it was infinity. If we were decreasing without bound, it was negative. So here is just a random example of an infinite limit. It's the limit as x approaches 2 of 1 over x minus 2 squared. And if you type that in, looked at the graph, it would be positive infinity. It would increase without bound forever and ever. It's an infinite limit because the limit, your answer, is one of the infinities. In this case, it's positive. And we also know with infinite limits that it's all about vertical asymptotes. All about vertical asymptotes. Those were a big deal because with those, you're either increasing without bound or decreasing without bound. Just depends on what direction you're going. Okay, so let me come over here and talk about limits at infinity. Limits at infinity. Believe it or not, it is different. It is different. And you really have to see the difference. Thinking about your quiz tomorrow, you know, I won't really specify this is an infinite limit. This is a limit at infinity. You'll just have to kind of know when you look at it. So here, and this is kind of hard to see up here, a little bit blurry, but this says the limit as x approaches infinity. That is positive infinity right there. The limit as x approaches infinity of 1 over x minus 2 squared equals 0. Let me show you the main difference between infinite limits and limits at infinity. With an infinite limit, your answer is one of the infinities. It's an infinite limit. However, a limit at infinity means that you are approaching one of the infinities. So you're either approaching positive infinity or you're approaching negative infinity. It doesn't necessarily mean that your answer is one of the infinities. This is just the direction you are approaching. Okay, so that's the difference. Answer is infinity, it's an infinite limit. If you're approaching an infinity, it's a limit at infinity. Now, with the limits at infinity that we're going to be dealing with today, we are more concerned about horizontal asymptotes. Horizontal asymptotes. And we actually spent some time in pre-calc last year talking about and finding horizontal asymptotes. It was the part that had like the 3 cases. We're going to actually do the 3 cases again today for the limits at infinity. All right, so the whole purpose of that is just basically to show you the difference. Infinite limits, limits at infinity. I'm going to put up here now the very, very, very important rules for finding limits at infinity. This would make excellent cheat sheet material for your quiz tomorrow. Just saying, there's some good stuff here. And I'm first of all just going to set up what the limit is going to look like. It looks kind of weird right now, but I'm just kind of putting it all together. So it's the limit as x approaches either positive infinity or negative. You're not actually going to see the plus or minus sign. That's just showing you it could be one or the other. And it's always going to be some kind of a rational function. And so this one just has ax to the m power divided by bx to the n. There could be more than one term on top or on bottom, but you'll see here in a second why I'm just kind of using those. Okay, first of all, let me explain what m and n are. And this again is a lot of stuff that we did in pre-calc for finding horizontal asymptotes. M is the biggest exponent of x on top, or in the numerator. M is the biggest exponent or biggest power of x on top. So you can probably figure out what n is. N is the biggest exponent or biggest power of x on bottom. Biggest power of x on top is m. Biggest power of x on bottom is n. All right. Now, just like we had 3 cases for finding horizontal asymptotes, there are also 3 cases for finding limits at infinity. So here comes the good stuff. All of the cases depend on m and n. So you kind of have to figure out what they are first. Now, case 1, you don't really have to call it case 1 if you don't want, but one of the cases says if m is less than n, so biggest power of x on top is smaller than the biggest power of x on bottom, the limit is just going to equal 0. I don't care if you're approaching positive infinity or negative. If m is less than n, your answer is 0, and you don't even have to do any work to show it. It's just 0. Now, next case says if m is greater than n, if m is greater than n, the limit is going to equal infinity or negative infinity. Well, how do I know which one? Is it going to be positive? Is it going to be negative? I'm going to put a little side note out here, which still might not make total sense until we try it with some of our problems. But to figure out which one it is, you want to plug in A. Now it says VBN. Let me explain what VBN stands for. A very big number. I got lazy. Plug in a very big number. Or what do you think VSN stands for? Very small number, to figure out which one it is. Again, you're still probably like, well, I still don't really know what it's going to be. Yeah, it's fine. Once we get to our examples, we'll figure it out. But plug in either a very big number or a very small number. I'll explain how you know which one, and that'll tell you if it's positive infinity or negative. So that's a case we'll have to kind of come back and revisit. Now, the only other thing that could happen here is, last case, if m equals n, so if the biggest power of x on top is the same as the biggest power of x on bottom, then the limit is going to equal a over b. A over b. Now, I haven't specifically said anywhere up here what A is and what B is, but you can kind of see from this format right here, A is the coefficient of the biggest power of x on top. B is the coefficient of the biggest power of x on bottom. Again, there could be more than one term on top or on bottom, but the coefficients of the biggest powers of x, those are what you pull out if m equals n. That's how you would figure out your limit. Okie doke. So everything depends on m and n. That's the first thing that I'm going to figure out with each problem. Okay, so directions, all they say is determine or evaluate each limit. On the quiz tomorrow, it's not going to specifically tell you that this is a limit at infinity, so think about your cases. That's something you have to pick up on. If you get to a problem tomorrow and it's approaching infinity or negative infinity, you just have to know that is a limit at infinity, and so I'm going to have to figure out which case it belongs to. So this is the limit as x approaches infinity of 3x plus 2 divided by 4x squared minus 1. Let me think about m and n real quick. M is the biggest power of x on top. Well, that's technically x to the first power, so we can go ahead and say that m is 1 here. A lot of times this is stuff that you just do in your head, but I'm writing it down in case you want to put it in your notes. And then biggest power of x on bottom is 2. So now we compare. M is 1, n is 2. That means m is less than n, because we all know 1 is less than 2. So if you look at your cases, that was the very first case that you wrote down. If m is less than n, the limit is just 0. So you don't have to graph it, you don't have to do anything fancy there. Anytime m is less than n, the limit will always be 0. All right. Not a lot of work to show on something like that, which is a bummer when it comes to partial credit. But again, if you are approaching one of the infinities, you got to look at your 3 cases. This is a limit at infinity. Let's keep going here. now it's the limit as x approaches negative infinity of 3x squared plus 2 all over 4x minus 1. Okay, well, biggest power of x on top is 2. M is 2. Biggest power of x on bottom is 1. So in this case, m is actually greater than n. Now we need to go back and think about our cases here. This was the second case that you wrote down. When m is greater than n, your answer is either going to be infinity or negative infinity. Well, to figure out which one it is, you wrote down on the side that you have to plug in either a very big number or a very small number. Let's talk about that part first. And this is where I immediately go. On this problem, our x values are approaching negative infinity. So you may actually want to write this down because it's kind of hard to remember later on why you did it that way. But this says, since we are approaching negative infinity, plug in a very small number, because negative infinity is a very small number. If it was positive infinity, I'd plug in a very big number. Now, you don't have to get real crazy here. To me, a very small number would be maybe like negative 100. I think I went with negative 100. It doesn't have to be that. It could be even smaller, or maybe even a little bit bigger than that. But that's usually my go-to VSN. Very small number, negative 100. So wherever I saw X up there, I plugged in negative 100. Now, we can keep going with this. If you want to just kind of type in the part on top and then the part on bottom, you'll see here in a minute why these numbers actually don't matter too much. But if you were to type in the top, you get like 30,002. And on bottom, you should get like a negative 401. Now, don't keep going with that to actually divide it out or go any further. Let me just kind of summarize what happened here. On the top, we got back 30,002. I would say that 30,002 is a very big number. Wouldn't you say that's a very big number? And on bottom, we got back negative 401, which I would say is a very small number. Now, hang with me here. I'm going to come down to the bottom and put just one more part to this rule here. Anytime you're working with very big numbers, very small numbers, here's how we make this one last jump to what our answer actually is. And I'm going to start with what we have over there. If you end up with a very big number over a very small number, your answer is going to be negative infinity. So if you want to go ahead and say answer to this example, example 2, it's negative infinity. If you had that switched, I'm just showing you all of the cases because you'll run into other cases later. If you end up with a very small number over a very big number, that would also give you negative infinity. And I'm going here, couple more. Let's say you get a very small number over a very small number, that is going to turn into positive infinity. That would be your answer. And then last but not least, a very big number over a very big number, that would end up being positive infinity. Here's kind of how I remember that. A very big number is positive. A very small number is negative. What is a positive divided by a negative? Negative. What is a negative divided by a positive? Negative. What is a negative divided by a negative? Positive. And you can kind of see the pattern there. It's something that you might want to put on a cheat sheet, but if you just think about positives and negatives, that should also make sense. So depending on what you're approaching, if it's negative infinity, go with a very small number. If it was positive infinity, I'd plug in a very big number. And then, like I said, these numbers specifically don't really matter. If you can just tell on top, when I square a negative 100, multiply it by 3, add 2, I don't know what it is, but I know it's going to be very big. And on bottom, when I take negative 100 times this, subtract that, I don't know what it is, but I know it's going to be very small. You don't really have to put that step down every time. You can kind of think ahead to what type of number it's going to be. All right, let's keep going here. That has to be the hardest case, case 2. Let's keep going though. Number 3 says, we need to find the limit as x approaches negative infinity of 3x squared plus 2 all over 4x squared minus 1. M and n. That's what I'm concerned about most at first. M, biggest power of x on top, is 2. N, biggest power of x on bottom, is also 2. So this is like the third case that you wrote down. M actually equals n here. So you don't have to worry about very big numbers, very small numbers. Look for the coefficient of the biggest power of x on top, coefficient of the biggest power of x on bottom. That's like your a and b. So all I have to do is put a over b, and that would be my limit. The limit would just equal 3/4. So, okey-doke. N equals n. Not nearly as much work for that one. I'm going to keep moving here. Stop me if you have any questions. Number 4, this is a good one. We have the limit as x approaches infinity, positive infinity, of 4x minus 1 over x. 4x minus 1 over x. I like to figure out m and n first. However, on something like this, you can't really tell what m and n are because it's not one rational function. You've got a fraction over here, and that part is not really a fraction. So what I would say you should do first here is get some common denominators so that you can turn that into one single fraction, not just part of a fraction. So I put the 4x over 1, and then looking at my denominators, the least common denominator would be x here. So if I just multiply that first fraction by x on top and bottom, this would turn into 4x squared over x. I went ahead and put that all together though. 4x squared minus 1. I didn't touch the 1 because it already had the correct denominator. 4x squared minus 1 all over x. You should really get it all together before you determine m and n. Okay, well, m, biggest power of x, on top is 2. N, biggest power of x on bottom is 1. If you had left it as two fractions like this, it would almost look like m is 1, n is 1. It would kind of look like m equaled n, but that's not right. M is greater than n. So this is the case where we have to do a little bit more work. I am approaching positive infinity this time. So I'm going to plug in a very big number instead of a very small number. Bless you. Since we are approaching infinity, positive infinity, plug in a very big number. All right, I usually go back to 100. It's not crazy big, but it's big. So wherever I see x up there, replace it with 100. Now again, it doesn't even really matter what that ends up being, that's just 100. But, you know, if you can tell, when you square 100, multiply it by 4, and then just subtract 1, it's still going to be a very big number. I went ahead and put what it was, but again, it doesn't matter. If you can tell, very big number divided by very big number, that is just going to give you positive infinity. It's like taking a positive divided by a positive, which is still going to be positive. Alrighty. Any questions so far? I think I just have one more here. So, last one. This one shouldn't be too bad. Number 5, it's the limit as x approaches negative infinity. It's a limit at infinity. And it's 4x squared minus 1 over x squared. It's a lot like number 4, but the bottom is now x squared. Anybody know what this one's going to be? 4, yeah. Since m is 2, n is 2, m equals n, so pull out a over b. b is technically just a 1, so 4 divided by 1, that will just give you a 4. Alrighty. We only have one example where m was less than n because that's just 0. You don't have to do any work for that type. Alright, let me go ahead and put the assignment up here. It is C27 from page 115. We're going to do 15 to 24. And I'll let you get started on that. Don't forget about quiz tomorrow. If you have extra time, you can do a half one-sided cheat sheet.